So right now I'm looking at a camera. So camera involves a lens, a shutter and a source of light. Like these, I have different optical instruments around myself day to day. I have microscope, I have telescope, I have binoculars, I have spectacles. So these are the different optical instruments which we use day to day life. Even the eye through which I'm looking at you is an optical instrument. So right now in this particular video we will be learning about different optical instruments which are kind of common and is an household name. So namely we will be studying about telescopes and microscopes. So let's watch out what are these telescopes and microscopes and the working principle behind them. Now we make our way into the final topic of discussion in this particular chapter of ray optics, that is optical instruments. How after we going through the different phenomena, a few of the phenomena associated with light, that is refraction, reflection, dispersion, scattering and all not, we will be using all these concepts to make up some optical instruments which will satisfy our need. Whether I want to look an object in a magnified sense, that is an enlarged image is wanted, or do I want to look up a very far off image, whatever. So based on that we will be putting up different tools at our disposal, mirrors, lenses and whatnot, so as to satisfy the purpose. So let's start off with compound microscope. So compound microscope is basically me having a lens over here and another lens over here. So as you can see, there is an objective lens where near which an object is kept, and another is I have an eye lens near the eye through which I actually see the object. So if you look closely over here, the object is placed somewhere between 2f0 to f0, that is between the center of the curvature and the focus. So between that, if I place an object, I am getting, or I will be expecting an image which will beyond C, and that to an enlarged inverted image. So that's what we will be getting. So if you look over here, this particular image, now this image will now act, or this is the final image which we will be getting, that is A dash, A triple dash, A B double dash. So this will be the final image which we will be getting. So from this point, the genesis of the light source, that is from the object, I end up getting an image A dash, B dash. Now this image which is formed because of the objective lens will now act as an object for the eye lens, eyepiece. Now the position or the distance between these two lenses are so adjusted such that it ends up following before the focus, or let's say between the focus and the pole, it ends up following in that particular range. So I end up getting in the same context, an image, a virtual image, and that too very enlarged version of it. So this is the final object which I will be or the final thing which I will be witnessing, and that is very large compared to what I already have. So the different parameters you should keep in mind is FO, FE, VO, U0, right? These kind of parameters, the object distance, the image distance, and the length between the two lenses, the eyepiece and the objective lens, and the height, the final height of the image, the height of the object. So make sure that you do keep in mind what are the different symbols which are used over here. Whenever there is a suffix O, it means I'm dealing with objective parameters. Whenever there is a suffix E, it means I'm dealing with the parameters associated with eye. So let's find out the magnification and other parameters which we can use to describe how good my compound microscope is. So in a nutshell, before moving down to discussion of the parameters, what I can do is summarize compound microscope as a whole.
So first I'll get an inverted image for an object placed between the radius of the curvature, the center of the curvature and the focus. Correspondingly, the image which I will be getting in an enlarged inverted image will now act as the source for the eyepiece. Now that position of that enlarged inverted image is such that that will give me, or that lies between the pole and the focus of the eyepiece, such that the image right now which we will get is an enlarged virtual image. So that's what compound microscope in a nutshell does. So angular magnification, or the magnifying power M, is given by, or magnifying power of the compound microscope is defined as the ratio of the angles subtended beta by the final image at the eye to the angle subtended alpha by the object seen directly when both are placed at the least distance of distinct vision. So basically, magnifying power is, let's say I have achieved a maximum magnifying power, that is, when I have placed my object at a particular distance and an image is at a particular distance, and I am playing with the length of the or the distance between the two lenses, moving them closer or farther from each other. So at a particular point, my image will subtend an angle with respect to eyepiece, right? The final image will subtend a particular angle, a field of vision with respect to eye. Now that the ratio of that to that of alpha is now a 0 point in consideration. That is, alpha is an angle when they are both placed at the least distance of let's say distinct vision. 25 centimeter is the least distance for distinct vision. So when I've kept both the lenses over there, the angle which they subtend right now is, let's say, a 0 point angle, or let's say a reference, and that is given by alpha. So beta is in general for a particular amount of magnification, but here is 0 count corresponding to alpha is least distance of distinct vision when both pieces are over there. So M is beta by alpha. Since angles are small, so alpha can be written to be tan alpha, or beta can be written to be tan beta. Now using those properties, in the triangle which I have just, in the diagram which was just shown regarding the compound microscope, I will end up getting the magnification to be this. Now D, they are kind of constant, so they will cancel out and end up getting me A double dash B double dash divided by AB. Similarly, moving on, so it will be first magnification due to the eyepiece multiplied with the magnification due to the objective lens. So it's the combination of both these things which will end up getting me the resultant magnification. So if I have a magnification, or the objective lens gives me a magnification of 3 and eyepiece gives me a magnification of 4, so in total I will have a magnification of 12, 4 into 3. That's what it suggests, and that's pretty evident. After this, what we did is simply multiply these two terms in the numerator and denominator. This is eyepiece, this is objective magnification. So ME is 1 minus VE by FE. It's quite simple, we can easily procure it. And ME is also equal to 1 plus D by FE. Remember what is D? D was shown in the diagram. So VE equals to minus D equals to minus 25 centimeter, least distinct of vision. Now moving on, now we look upon the objective lens, that is its magnification is V0 by minus U0, and again the similar parameters which we have found out for the eyepiece we will now have to do for the objective lens as well, with these assumptions taking place, that is very close. So U0 is equal to F0 and V0 is almost equal to L. So again the total magnification comes out to be this, simply trying to express it in the parameters which are already given in the setup. That is, there are no parameters which we find it actually quite difficult to find out. Focal length of eyepiece, focal length of objective lens, distance between the two lenses, these of distinct vision, these kind of things easily procurable. So that's why we always try to express whatever parameter or whatever physical quantity which we want to study in the terms of measurable quantities. So these quantities, these are measurable quantities. So normal adjustment, that is that image at infinity, this condition will come out to be this almost equal, again means approximations are in place. So the key aspect in optics is always make sure when and what assumptions are being put into place. It is very crucial, right? This from just based on this particular mathematical expression, I can play you along. Without giving assumption, if you straight away work out this in a particular numerical, and in the numerical it wasn't made based on an assumptions, you will end up getting a screwed up answer. So you don't want to do that. So make sure whenever you write up a particular mathematical expression, the corresponding assumptions are written side by side, such that you are able to get hold of when to apply that particular expression if the assumptions are given or not. Now, astronomical telescope, that is, I need to see the objects which are very far from me. So again, similar arrangement to that of the microscope, but just on the flip side of it, my objective lens is having a higher aperture or higher, it's a big, because I want to absorb the maximum amount of lights coming from a very far off object, because there are quite a few light rays coming out when the object is very far. So I want to make sure that a good amount of light rays, they are coming in and are being used up. So as the object is at a very far off place, so it means the light rays will be coming from infinity, that is a parallel set of light rays will be hitting my objective lens. So the objective lens and the eyepiece, they are set up in such a manner that I end up getting the image at infinity, and highly enlarged image. So the image which the object lens forms must be at the focal length of the eyepiece. So the objective lens forms an image at the focal point of the eyepiece, and we end up getting the image at infinity, a highly enlarged image. That's how the telescope works. Now again, the angular magnification or the magnifying power of the telescope again tells me the same thing. Ratio of the angle subtended by the image at the eyepiece as seen from the telescope to the angle subtended by the object as seen directly when both of the object and image are at infinity. Now for telescope, I'm looking for the objects at infinity. For compound microscope, I was looking for the objects placed at the least distance of distinct vision. So please make sure the conditions are properly held on with it whenever we are talking about astronomical telescope and compound microscope regarding magnifying power. So please keep that in mind. What is magnifying power in telescope and what is magnifying power in microscope? Again, we will work out the similar calculations over here. So again, the angles will be very small. I can use up with that assumptions regarding tan beta and tan alpha being simply replaced as beta and alpha. Similarly, the magnification, if you can work it out, we will find out the magnification is the ratio of the two focal length and the negative of it. And this is a very important condition for working of telescope, that is the focal length of the objective lens and the focal length of the eyepiece has to be equal to the length of the telescope. This is a very important point, so please keep that in mind whenever you work out any problems regarding astronomical telescope. Now, image form at least distance of distinct vision. Now, this is what we actually need. That is, this is the other end point of the telescope which we are trying to find out. Because if at all we end up getting the image form not let's say less than the least LDDV, then I won't be able to see that image properly. So I need to make sure that my image gets formed over here at the point B. AB is the image which I need to form. So astronomical telescope, again, these are things which we have already done. Again, it's simply a repetition of it so as to make you understand what's happening around. So through lens equation we end up getting this. That is, right now we did again the same amount of things. Why? The reason behind was to only find out the necessary condition for me to see the object at this point. Least distance of distinct vision. So similar, or we work out in exactly the same fashion in which we started studying the magnification of the astronomical telescope. For that, the only thing which we changed for arriving at the conditions for LDDV, least distance of distinct vision, was to just place an D, that is the let's say LDDV, over in the expression. That's what we all needed to do over here. In place of V, I substituted this and end up getting this. Now, obviously, now we will try to work out some mathematical operations on that particular equation, multiplying f naught on both the sides, and simply we rearrange it. We end up getting the magnification to be this. Now, why did we end up putting up so much effort for finding out the relation relating to the parameters of the telescope, FO, FE, L, and everything like this, in terms of least distance of distinct vision? Because I want my magnification to be in terms of physical quantities which are very good or which are very easy to measure up, and also I don't need to put up with extra refractive index or any new parameters. I simply need to measure it up, that's it. So clearly the focal length of the objective must be greater than that of the eyepiece for larger magnifying power. It's pretty evident from the expression. So it's just mathematical expression put to words. Now, also it is noted that in this case, M is larger than that in the normal adjustment position. That is, we were trying to make sure that the object which we will be seeing through telescope lies in the least distance of distinct vision. But what we got as a reward is the object in that particular condition has a greater magnification than in a normal adjustment. So obviously our magnification kind of increased, and also I am able to see the object very clearly, and I have decided, or I have come across the limit of that. Now a Newtonian telescope. Now this is Newtonian, as the name suggests, belongs to Newton or his version of telescope. So this is actually a very simple and founding stone as far as the technology of telescope is concerned. So Newton basically used mirrors when he wanted to know more about the stars, to look at in a very good fashion. So this is how we use it. So the light from the star, they enter this region, and I have a concave mirror placed over here. So after reflection, they will be trapped inside by a plane mirror. So the light coming from infinity gets reflected from a concave mirror, hits the plane mirror, then undergoes multiple reflection over here. Then I have an eyepiece, then I can directly procure the image. So this is how the Newton actually used to see the far of celestial objects. And obviously it's a reflecting time because I'm only using mirrors for these. So magnifying comes out to be FO by FE, same as that in the previous case. Resolving power of microscope. The resolving power of microscope is defined as the reciprocal of the distance between the two objects at which can be just resolved when seen through the microscope. What happens usually while seeing through microscope is it's very hard for me to differentiate between one value to the other value. So the resolving power tells me, or is a parameter through which I can make sure that I will be able to properly distinguish between two sets of information. That is, this value corresponds to a particular data and this value corresponding to a different data. I'm able to segregate the different information. So that is resolving power of microscope. So if higher the resolving power, so it means I can separate very closely data easily. If it has a low resolving power, it means I cannot distinguish between the two objects very clearly. I don't know whether those two objects are lying on each other or they are one and the same. But if my resolving power is high, then I can easily differentiate them. And that's the resolving power. So it's like this. So let's say there is a small organism over here and there's a small organism over here. If my resolving power is good enough, so I can easily separate them, consider them as two distinct points. But if they are related, they are very close to each other, then I might think them to be as one single dot. In that case, I have my less resolving power. So this is an objective. So right now what we are trying to do is come up with a mathematical expression for resolving power. So the resolving power, as the definition suggests, is 1 by del D. So it's 2 mu sine theta by lambda. It depends upon the wavelength of the light as well and the refractive index of the lens through which you are observing it. And theta is kind of a measure of aperture, how big the lens is. Now resolving power depends upon the wavelength, refractive index of the medium, half angle of the cone of the light from one of the objects, theta. So that's resolving power. So resolving power is very important as far as it's concerned with observing objects under a microscope, because the magnified images which are being witnessed, I need to make sure these two data are separated, because if they are not separated, that or the resolving power is not good enough, then I might clearly miss out the distance between these two particles, which might be of very important parameter or very important aspect in my calculation. So the resolving power of microscope is very important. It should need to be very high in order to have that. So I can play along with these parameters to increase my resolving power. Now, resolving power of a telescope now is defined as a reciprocal of the smallest angular separation between the two distant objects whose images are seen separately. So as the name suggests, resolving is I am able to see the two objects distinctly. It doesn't seem to me that they are one single object. It clearly seems to me that they are two separate objects. So then the angular separation between those two objects, which I am able to see clearly, that is the resolving power of the telescope. So again, these are the 2 points. An objective lens, d theta, is basically the resolving power of the telescope, which in turn is equal to a by 1.22 lambda. So a by 1.22 lambda is the resolving power for a telescope. Again, wavelength lambda and diameter of the objective, how big my lens is.
Now we just concluded everything which we have studied so far in ray optics, different phenomena which we have studied, reflection, refraction, dispersion, and everything in ray optics has been summed up in the application part which we just concluded regarding microscopes and telescopes. I studied about compound microscope, compound telescope, that is, it might be having different names, but we have studied all those things right now. So we have just wrapped up also the application part of the optical phenomena which we studied in this particular chapter.